Let's say that you have a number of machines that are all working together on some common collective task. It doesn't really matter what these machines are. What's important is that they all do the same thing. They are all contributing equally to the task. This could be something simple like, light bulbs illuminating a room, or disk drives in a data storage center, or maybe they're elevators servicing a skyscraper, or I like to think of as toilets in a sports stadium. But whatever this task is, you also have some minimum target that you need working just to get the job done. But of course, because machines have this tendency to break down at inopportune moments, that can reduce the number of working machines to below your minimum target number. So it's always best to have a few extra machines around handy just to increase the overall reliability. Now, because you are in this field, you also have more information to work with. You know the reliability of each individual machine, just based upon how old each one is or what condition each one is in. And so each machine can have its own individual reliability score, the chance that it will continue working without breaking down. So the overall problem is pretty simple to understand. Given the fact that you have a number of machines, and each one has its own known reliability, and you have a minimum target number that you need working, what is the collective reliability of the entire set? How do you combine all of these reliability ratings into one number? What is the chance that your minimum number of machines are going to work? It can be any combination of any of these machines, as long as it's just the right number of them. This is the collective reliability problem, and it is a real-world problem that shows up in facilities management. Hi, my name is Thomas Foote, and I work in facilities management, and this problem actually showed up. But is there a way to solve this? Well, yes. As it turns out, there's a very simple, easy-to-understand method to calculate the collective reliability of any set. How easy? So easy it barely deserves its own title graphics. Let's start with this simple problem. We have three machines, one that's got a 90% chance of working, one that's got a 60% chance of working, and one that's got only a 25% chance of working. And we want to know what is the chance that two or more of them are going to work. So how do we figure out the collective reliability? How do we figure out this chance that at least two of machines will work? Well, it's a simple four-step process. Step 1. We list out all the possible outcomes. This means we create a list of everything that can happen, all of the possibilities of our machines working or not working. This includes everything from all of the machines working down to all of them failing, and every possible combination in between of some of them working and the rest of them failing. And in this case of three machines, there are 8 possible outcomes displayed here in these 8 rows of checks and crosses. Step 2, we identify the desired outcomes. That means that for each outcome, we count the number of successes. We are only interested in 2 or more successes, so we're only really concerned with these 4 outcomes here. So we could just get rid of the others. Step 3, we calculate the probability of each outcome. That's easy. Each time we see a success mark, we put in the chance of that machine working. And wherever we see a failure mark, we put in the chance of it failing. And that's just 100% minus the chance of success. And then we multiply across horizontally. Step 4, add them up. There. And we are done. The collective reliability of this set reaching our target of 2 or more successes is 64.5%. Great. So we have a problem and we have a solution. So why this video? Well, as it turns out, there is a big problem with this solution. How big? Big enough it gets its own title graphics. Let's take another look at our problem. The big problem occurs back here in the first step, and it's got absolutely nothing to do with whatever our minimum target is. The problem is what happens when we try to apply this solution to larger sets. Well, look at what happens when we add just one new machine to our set. Our first step is to list out outcomes. Well, how many possible are there with 4 machines? Well, we know that with 3 machines, we have 8 possible outcomes. So that is 8 possible outcomes with that 4th machine working, and 8 possible outcomes with that 4th machine failing, or 16 possible outcomes. And if we add a 5th machine to our set, that means there are 16 possible outcomes with that 5th machine working, and 16 possible outcomes with that 5th machine failing, or 32 possible outcomes. If we add a 6th machine, that's going to be 32 plus 32 possible outcomes, or 64 possible outcomes. Every time we add a single machine to our set, it doubles the number of outcomes we have to look at to solve this problem. And in the field of computer programming, we have a very specific term for this issue. We call it an exponential increase in time complexity with the big O notation of 2 to the nth power, which is, well, let's face it, that is technical gibberish. I mean, what does this mean? What does this mean in English? I'll explain. It means this problem can quickly become too big to solve. So what I've got here is a Python program. And don't worry, you don't need to understand Python or programming to be able to follow along here. I'll explain what you need to know. There's a function here at the top. This creates a random set of machines for us to work with. So if I say, give me a set of size 5, it'll come back with 5 numbers. Each number is like randomly selected between 0% and 100%. So these are going to be the reliabilities of the machines. This part here is a function that does that 4-step process that I just described to you that calculates collective reliability. I'm going to pass it the set of machines and their reliabilities. I'm going to give it a target number, which is going to be half the size, and then it's going to calculate the collective reliability. Down here at the bottom, we've got our main test loop. What's going to happen is starting at a size of 1 and going all the way up to the size of 50, it's going to create a new set of machines of that size. Then it's going to see what time it is currently. Then it's going to calculate the collective reliability. And it's going to take that result and toss it in the trash. We don't care what that result is, because then we're just going to take another look to see what time it is and then print out a report saying for this size, it took this much time to solve the collective reliability problem. So let me show you what happens when we run this program. So as you can see what happened when I started the program, it finished like the first 15 or so within like the first eye blink, and wasn't until like about 16th or so that it was actually starting to take enough time that we could notice it. And as you can see, as we continue on to process the larger sets, it's taking more time. Specifically, if you look at these numbers here, they're actually taking roughly twice as much time for every time we increase the size by 1. And that's the problem of this exponential increase in time complexity. I mean, we're not just doubling the amount of outcomes we have to look at, we are doubling the amount of time it takes to solve the problem every time we increase the size of our set by just 1 element. So, like, how long is this going to take to solve to run this entire program? Well, let's see. Let me do a quick calculation here. We're going to use 18 as a base. 1.39 times 2 raise the power of 51 minus 25 minus 18. So this looks like it's going to take about 355 years for this program to complete running. Let me stress that again. This is over 3 centuries that this program is going to take to complete. And obviously this, well, as a famous woman on the internet once said, ain't nobody got time for that. So this method works fine for small sets, but if we want to solve for larger sets with hundreds or even thousands of machines, we need a different method. This is the problem that intrigued me. Let me show you how I solved it. Let's start with this sample problem. We have these 7 machines, each with its own reliability, and we want to know what is the chance that 4 or more will work. Well, I thought about it like this. Let's make a copy of this problem and change just one detail in it. There, I've changed the first machine to have a 100% chance of working. How does this affect the problem? Well, first of all, we know that the answer to this new problem will be larger than the answer to our original problem just because the new reliability values are either larger or the same as the original values. And we also know that because this first machine has got a 100% reliability, then the first machine is going to work, no question about it. And if there's no question about it, this can be taken out of the question. So now we're looking at a new problem. What is the chance that the remaining 6 machines will reach our minimum target? But there's one other detail here. Our first machine worked, so it's fulfilled one of our target. So the target is no longer a minimum of 4. It's now a minimum of 3. And we can make the same argument in the other direction. If we create a new copy of our problem and drop the first element's reliability all the way down to 0, we know that the answer to our new problem is going to be lower than the answer to our original problem. And because this first machine has a 0% reliability, it's going to fail, no question about it. So we can take it out of the question. And because our first machine is failing, it doesn't help with the target, so the target stays the same. So what is this telling us? Well, we know that the answer to our original problem is somewhere between the answers to these 2 problems. So our answer must be somewhere between the answer between these 2 problems. More specifically, it's going to be some percentage between these 2 answers. What percentage? It's going to be this percentage over here. The success rate of our first machine. I mean, just think about it. If we try turning on just that first machine, we have a 90% chance that it will work, at which point we've transformed our problem into this one, where we only need 3 of the remaining 6 to work. But if our first machine fails, we've transformed our problem into this one, where we need 4 of the remaining 6 to work. So the answer to our original problem is going to be 90% times the answer to this problem, plus 10% times the answer of this problem. I call this the simplification rule, which states that the collective reliability of any set is equal to the reliability of the first element times the collective reliability of the rest of the set reaching 1 fewer target, plus the fallibility of the first element times the collective reliability of the rest of the set reaching the same target. And yeah, I get it. I know that is a huge mouthful of words to label with the word simplification. I can see the irony here, but I'm not expecting you to remember all of these details. For right now, I just want you to remember this one detail. We can find the answer to a large problem by finding the answers to 2 smaller and simpler problems. So I can find the answer to this problem if I can find the answer to these 2 problems. So How do we find the answer to these two problems? Well, these are collective reliability problems too, and the simplification rule applies to them. So to find the answers to these two problems, we just need to find the answer to these four. Well, how do we find the answer to these four? Oh, that's simple. We just need to find the answers to these 8. Oh, wait a minute. I hear you cry. 1, 2, 4, 8. This is doubling in size for every element in our set. And yes, this is true. This is the same huge problem we have in the original 4-step method. And it is unavoidable at this stage of analysis. But this is giving us a new way of looking at this problem. We've already found one very interesting rule, the simplification rule. Let's look around and see if we can find any others. Let's take another look in this case of 7 elements, target of 4. But I need more space on the screen here, and I don't really need to see all the numbers all the time. All I really need to know is the number of elements in each set, and so let me just replace that here. Actually, we could put both of these in the same label here. I don't even need to see the words. That's way too big. Perfect. There. This is our starting problem of 7 elements with a target of 4. And we know from the simplification rule that we can solve this problem by solving these other 2 smaller problems. Now, there are 2 paths that we can follow here. The top path, which I call the success path, and the bottom path, which I'll call the failure path. The problem in the success path is 1 element smaller and 1 target smaller. So let's follow this success path and see where it goes. Now, as we expand this tree, we can see that as we progress up this path, the elements and targets are dropping until we reach this interesting point here at the 3, 0. What's happening here? What does this mean in English? This means that we have a problem where we have 3 machines with different reliabilities, and we want to know what is the chance that 0 or more will work. And if you go through the whole 4-step process here of listing the outcomes, you can see that the worst case outcome has 0 successes, which is acceptable. In fact, all of the outcomes are acceptable. And if you spend the time doing all the math and adding all the probabilities and all the outcomes, you're going to get 100%. And this will always be true, regardless of what the individual reliabilities are or how many elements you have in the set. If the minimum target is 0 and you break down all of the outcomes and calculate them and add them all up, you will always get 100%. And this is a waste of time. So we can replace this with a simple golden rule, the 0 target rule. If the minimum target is 0, the collective reliability is 100%. We can make the same type of observation if we follow the failure path. As we traverse this path, we see the number of elements dropping, but the target stays the same. And eventually we see the problem, this one here, 3, 4. This one looks kind of weird. What does this mean in English? Well, it means we have 3 machines, each with their own reliability, and we want to know what is the chance that 4 or more will work. And if you run through the whole 4-step process, it's a waste of time because no outcome will ever have enough successes in it to reach the minimum. There aren't enough machines in the set. So we can just skip this whole process and replace it with another golden rule, the high target rule. If the minimum target is greater than the number of elements, the collective reliability is 0%. So these 3 rules are enough to calculate reliability. Let me show you how this works. Let's go back to our really small problem of 3 elements, target of 2. Now all we have to do is every time we see a reliability problem, we go over here and look at the 3 rules that we have to work with and just see which rule applies to it. We've got 3 elements, target of 2. That's not 0 and that's not high. So it's the simplification rule. So we split the problem. Here I've got 2 elements, target of 1. It's not 0, it's not too high. Simplification rule. Here I've got 1 element, target of 0. That's the 0 target rule. So we know that's 100%, and we might as well do the math along the way. Here I've got 1 element, target of 1. That's simplification rule. Here I've got 0 elements, target of 0. And they may look weird, but that falls under the 0 target rule. And do the math. Here I've got 0 elements, target of 1. That's the high target rule. Just do the math, and we might as well, we add them up, do the math, add them, multiply. We're making progress. Down here, we've got 2 elements, target of 2. That's the simplification rule. 1 element, target of 1. That's simplification rule. 0 elements, target of 0. That's our 0 target rule. 0 elements, target of 1. That's our high target rule. Down here, I've got 1 element, target of 2. That's our high target rule. And it all collapses down to that, which we've seen before. How does this compare with our original 4-step method? Well, back here in the Python, I've replaced our 4-step collective reliability function with this new 3-rule recursive function. And if you are a beginning programmer and you may have heard about this recursion thing and how difficult it is to kind of wrap your head around, this is a good example of a recursive function. So I suggest you study it. And if you're not a programmer, just take comfort and pleasure in the fact that you don't have to learn a thing about recursion to be able to lead a rich and fulfilling life. But let's run this program and just see how it works. Okay, it's working, and it actually works a lot faster than our original 4-step method. You can see we got like up to the 23rd element set in just about a second or so. Originally, it was taking a little over a second to figure out an 18 element set. So this is like about 30 or something times faster, but it's still, you can see it's still suffering from this same problem of taking twice as long every time the set grows by 1 element. Let's do a little math here. Okay, 23, 1.07 times 2 raised to the power of 51 minus 25 minus 23. So this program is going to take about 8.5 years or so to complete. That's a lot better than 355 years. We're making progress. That's good. Let me show you some other stuff I found. The last time we looked at this diagram, we found these 2 rules. Let me show you a few other rules I found. Let's start by clearing some space and then focus in on this problem here, 4 elements, target of 4. If we break down the outcomes, we can see that there's only one outcome that we're interested in. And this is going to happen regardless of how many elements are on the list. As long as the target is the same as the number of elements, there's only ever going to be one outcome we're interested in. So it's a waste of time looking for any of the others. In these cases, we should just simply focus on the top outcome and calculate it. So we can turn this into a new golden rule, the equal target rule. If the target equals the number of elements, the collective reliability is the combined product of the individual reliabilities. And we have another interesting one up here at 4 elements, target of 1. If we go through the 4-step process, we can see that we want the sum of all of these outcomes. And that is a lot of math to go through. But there's a shortcut. Instead of doing all that math, we just take advantage of the fact that all of the outcomes adds up to 100%, and this is what we want, and this one row is what we don't want. So all we have to do is look at that last outcome where all the machines have failed, calculate it, and subtract it from 100%. That will give us the same answer. So we have another new golden rule, the one target rule. If the target equals 1, then the collective reliability is 100% minus the combined product of the individual failure rates. Technically, what we are calculating is the chance that none of them works doesn't happen. So what happens if we use all 5 rules to solve a problem? Well, it goes a lot faster. Look, here's our 3 elements target of 2 problem. That's simplification rule. Here we've got 2 elements target of 1. That's our one target rule. Got a formula for that. Over here we've got 2 elements target of 2. That's our equal target rule. Got a formula for that. And we're done. Back over here in Python, I've added our new 2 rules, equal target rule and one target rule, to our recursive function. And let's see what happens when we run this. And now it's doing size 24 in about 1 second. It's going twice as fast. So now this program's going to take maybe only about 4 or 5 years to complete. More progress. So there's one final and very important rule in this process that I need to show you, and it's what happens in the middle of the diagram. So let's start at the root of our 7-element target of 4 problem, and then we follow the success path, and then we follow the failure path. And what we get is this problem here, 5 elements, target of 3. If we start at the root again and we take failure and then success, we get this. 5 elements, target of 3. These 2 problems are the same problem. The same numbers are going in, the same number is going to come out. And calculating this twice is obviously a waste of time, and you might think that if we do something to avoid calculating things twice means we're going to double our speed again, but no, that's not the case. It's far better than you would expect because this duplication issue is far worse than it appears. Let me show you how large this problem actually is. This is a full breakdown of our 7-element target of 4 problem. Some of these problems are unique problems that need to be solved, and others are duplicates. I'm going to highlight here, these are the unique problems that need to be solved. I colored them green, then I went back and added sparkling effects because I realized some of you may be colorblind. These problems definitely do need to be solved. The others, which I highlighted in red and then set on fire, are duplicates of unique problems. And at first glance, it may look like there's about the same number of unique and duplicate problems, but no, that's not what's happening. We actually have 15 unique problems and 24 duplicate problems. Fully 60% of our work here is wasted effort. And this duplication issue becomes worse as our initial problems get larger. Here is a breakdown of 8 elements target of 4 problem. There are 19 unique problems in this diagram, but 50 duplicates. Remember that there were 24 duplicates in the last problem, and I just increased the number of elements in our set by 1, and it doubled the number of duplicate wasted effort. This trend continues. This here is 9 elements target of 5. We've gone from 50 duplicates to over 100. Here's 10 elements target of 5. We're now at over 200 duplicates. Here's 11 elements. We're now at over 400 duplicates. Here's 12 elements. Over 800 duplicates. You get the picture. So how do we solve this? Simple. We use this technique. It's called memoization. which is just this fancy term invented by some programmer who obviously got paid by the syllable. It basically means that we just use a memory structure to store answers when they are solved and then pull the answers from when the same problem comes up again. Here, I've got my memory structure added to our function, and I've added 2 new rules here. Here's one. First, simply checks to see if this particular combination is already in the memory, and if so, it returns the value from the memory. If not, we calculate the reliability and we store it in memory. Watch what happens when I run this program. Let me do this again, only this time let's make things obvious. This program has finished. It calculated values so quickly it completed the entire program before we even noticed it happening. We've completely broken this exponential increase in time complexity condition. If I go in here and I change the range of numbers, go up to say 500 and run this again, you can see that it's now calculating sizes that were unimaginably large just a few minutes ago. The sets are certainly taking more time to calculate as they get larger, but it's no longer doubling in time with each new element. And by all rights, this should be the end of this video. We have cracked the exponential time increase. I should just be able to end this saying, this is how we calculate collective reliability for large, diverse sets. But unfortunately, let's run this again, but really push it to the limit. We're going to start at 100 elements and calculate up to about 5,000 elements, going up in 100 element increments. Watch what happens when I run this. There, the program has crashed. When we try to calculate a set of 1,000 elements, Python crashes at this point, and then we get this error message here. It says recursion error, maximum recursion depth exceeded in comparison. So I have tested this solution using several different languages and several different operating systems, and no matter what I use, there's always this point where the program just crashes. The exact point where it crashes changes depending upon the language or the operating system, but they all crash for the same reason, which I'm not going to get into because, well, look at it. Look, if you are a programmer, pause here, read this, but if you're not a programmer, all you really need to know is that the way most languages manage memory makes them not capable of doing these deep recursive dives. And they hit a point where they just can't go any further. So what do we do about this? Well, it turns out that there are 3 different things we can do. First of all, we can just find a better language. There's probably a language out there which handles stack memory differently. I'm thinking maybe Lisp or Prolog could do it, but I just haven't tested them yet. Increase the stack space. Just research the language. Usually these languages have a setting in there where you can change the stack space. And this will work. If you double the amount of stack space, it won't crash at 1,000 elements. Now it'll crash at 2,000 elements. But this is just kicking the can down the road and making it somebody else's problem. I think that's the wrong way to solve problems. Then there's this. Rewrite the program. Specifically rewrite it so it doesn't use recursion. That's what I did. Let me show you how I approach this. Let's take another look at our original 7-element target of 4 breakdown. Now, we had found that some of these subproblems are unique problems, and the rest are duplicate wasted efforts. So I thought, as long as we're avoiding the duplicates, let's get rid of them and tie up the loose ends and straighten things out. And what we're left with is this very nice looking lattice structure. And what our recursive program was doing was it would start here at the root of our structure, and it would run through this long meandering path through all the subproblems, where every time it moved from left to right, it eats up some of the stacked memory. And when it moved from right to left, it replenished the stacked memory and returned with the value. And I realized that our new problem was that number of times it was running left to right. And the easiest way to solve that problem was just simply never do that. Because what I saw in this structure was that calculation basically flows from right to left. If calculation goes from right to left, why on earth was I starting over here at the far left? I should start calculating things on the far right. This led to a process I call the lattice weave. And here we have our structure. We have our 5 rules and the individual reliabilities and failure rates of each element in our set. The process basically runs through this structure in columns from right to left, and I actually found it a little easier to program and to understand if I expanded the structure just slightly. We start by recognizing that the top 2 subproblems with targets of 0 are handled by the 0 target rule, and so we don't need that rule anymore. Down at the bottom, we have 2 subproblems where the target number is greater than the number of elements. So that's handled by our high target rule. Don't need that anymore. On the far right, we have this one, 2 elements target of 1. That uses the failure rates of the last 2 elements in our set. That's our 1 target rule. Over here, we've got 2 elements target of 2. That uses the success rates of the last 2 elements. That's our equal target rule. Everything else from here on is the simplification rule. In every column for each subproblem, we simply pull the success and failure rates for the corresponding element and combine those with the 2 linked problems. So here we have 3 elements target of 1. That's going to be using these 2 values combined with these 2 values. Three elements target of 2. These 2 values combined with these 2. Three elements target of 3 using these 2 values combined with these 2. And we just continue on. Everything in the 4th column here, I should say, uses these 2 values combined with values found in this column. And we just continue on. And here it is. Here's our answer to our problem. Given these 7 elements, all these different chances of working, what is the chance that 4 or more are going to work? 69.7%. So back here in Python, I've replaced the recursive method with the new lattice weave method. It's fairly large. Here we go. There we go. So it doesn't fit on the screen all at once here. But I'm going to run this all the way up to 5,000 elements. And as you see, it's just chewing through this. It just shot right past 1,000 elements, now past 2,000 elements, and it's going so much faster than our original recursive method. And it didn't crash at 1,000 elements, and that's not going to crash because it's not using any stack space. Now, there's one other thing I wanted to show you about the lattice weave method, and then I will let you go. Let me load this up here. This is a modified version of the lattice weave method. It's much smaller here. It only takes the elements that set coming in. It doesn't take a target value. It doesn't focus in down to a single target. Instead, what it does is it kind of branches out and tries to fill that lattice as much as possible. A result will look like this. If I give it a 20 element set, it will figure out all of this stuff. And in the method, we'll then return this entire final column here. And this is something I call the reliability spectrum. You can graph it out here and see what it looks like. This can be used to answer more general questions like how many of these machines can I expect to work with any given level of certainty. And yeah, it sure does take a little more time to calculate, but now we're calculating so fast we can afford to spend a little more time to get the entire picture. And that's it. That's the lattice weave method, the way to calculate collective reliability. So I hope you enjoyed, or at the very least learned something valuable from this video. If you have any questions, I'd be happy to answer, so just leave a comment below. Also, I've put the code on GitHub, so you can take a look at it. I don't know what else to say in an outro, so I'll just trust the guy who does my graphics to put something dignified on screen. Take care.